Review for the Unit 7 test. The first question they're asking is the degree of each vertex. When you look at a vertex, you count the number of edges that are going into that vertex. So for this first one, it would have a degree of 2. C, therefore, would have a degree of 3, and E would have a degree of 5, because there's 5 edges going all the way around. Also, B has a degree of 3 and D has a degree of 3, and I'm going to come back to that idea later. It says, how can you quickly determine whether a graph has a Euler's circuit? In order to have a circuit, all vertices have an even degree. So all vertices have an even degree. So that's for a Euler's circuit. For a path, Euler's path, that means only 2 vertices are odd. So to have a circuit, they're all even. To have a Euler's path, only 2 vertices are odd. So in this particular case, since we have 1, 2, 3, 4 vertices that are odd, that would mean that this is neither a path, Euler's path, or Euler's circuit. So on the line below, it asks us to determine whether each graph below has a Euler's circuit, and just answer yes or no. So real quickly, you'll see that there are, this first vertex here has an odd degree of 3. So the answer is simply no. Remember, they all have to be even. Here I have a degree of 4, here's a degree of 4, degree of 2, degree of 4, degree of 4, and a degree of 4. So notice that all of these vertices are even, therefore the answer is yes. And this last one, again, as long as we have even one vertex that's odd, then the answer is simply no to a circuit. The next question is asking, how do we know if a circuit is a Hamiltonian circuit? The difference here is that, remember, a circuit, all of the vertices are even. In a Hamiltonian, that means that you start and end at the same position, and you use all of the edges exactly once. So you do not have, does not have to use all the edges. So you can start and go back and not use all of the edges. All right, the next problem here has to do with coloring. It says the minimum color, the rule of thumb, is you can color any 2 areas as long as they do not share a side. So you always want to find the least number of colors, or the minimum number of colors that you can do that in. And they have the outside region here as 5, and so since that touches all of the areas, this would take 3 colors. It's also known as its chromatic color. Here, same thing. We want to just color as many as we can with as few colors as possible. And for this particular one here, we're going to end up with 4 colors. So it has a chromatic coloring of 4. And literally you can do that by simply coloring if you would like. All right, this next question is a little bit more involved. It has to do with creating an activity graph. And to create an activity graph, the first thing you want to do is you're going to start somewhere. Then you're going to look at all the things that don't have a prerequisite. So in this particular example, A and C do not have, or A and G do not have a prerequisite, and neither does C. So that means each of those can start off their own path because there's nothing that needs to come before them. You'll notice here that B has a prerequisite of both A and C. So after you do A and after you do C, then you can do B. So that takes care of that. And then D has just a prerequisite of C, so that we can put our D there. So that takes care of that. E actually has a prerequisite of D and G. So that means that you have to complete D and G before you can perform task E. F has a prerequisite of E, so once you're finished with E, you can perform F. H also has a prerequisite of E, so that can also follow E. And I has a prerequisite of B. Now, J, you have to finish F, H, oops, I typed the letter B there, sorry. You have to actually finish all three of these things before you can do J. And then the only thing left is K. And K, once you're finished with G, you can do that as well. And then right here is the finish. So this is how you actually draw the path. Now once you draw the path, what you want to do then is put the amount of time required to complete that path, or each component. So A takes 4 hours, B takes 8 hours, I takes 8 hours, and J takes 5 hours. So the top path, A, B, I, and then J to get the finish, has a total of 25. So A, B, I, J has a total of 25 hours. So then our next path would be to start with C, which is 2 hours. Now we know we can go C to B to I to J, and those numbers are already there, so that's going to take me a total of 23 hours. So that's our next path. The one after that, we have C and then D, which will take 9 hours. And then we want to follow that down to E, which is 4 hours, H, which is 2 hours, and then we already know J. So this path is C to D to E to H to J. And that particular path there is going to be a total of 22 hours. The next path that we want to look at is C to D to E and now F. F has 3 hours and then J. So that's C to D to E to F to J. And that gives you a total of 23 hours. And then we have the paths along G. So we have 2 paths that follow G. G, the required time for G is 6 hours, and then we have G to E to F to J, and that is going to be 18 hours. I'm going to put these paths up on top here. Then we also have G to E to G to E to H to J. And that's going to be 17 hours. I'm getting that by going 6 plus 4 plus 2 plus 5. That's 17 hours. And then our last path is just G to K. And K is going to take 7 hours. So the path G to K is 13 hours. So this is called an activity path. So you draw the graph, draw out each of the paths. You can always tell how many different paths you have. You have all these different forks here. And that tells you how much time you have for each of the paths. So then once you've done that, you're ready to answer the questions. The first question is, what is the PERT analysis to determine the critical path and the minimum project time? The minimum project time will always be the length of the longest path, because even though these activities can be happening at the same time, the longest path would be your minimal time. So the longest path, which is A to B to I to J, which takes 24 hours. So that would be your longest path. says, can activity D be delayed without affecting the project time? Now, what you want to do is go up here and look. It is one of the shorter paths, and since it doesn't affect the other path, the answer is yes, that it can be delayed by that paths involving D, the longest path is 23 hours. So since that's less than 24 hours, the answer is yes, you could delay it by 2 hours and still be successful to end on time. And then question C says, can activity I be delayed without affecting the project time? Now, I is part of this critical path here, so the answer is no. If you delay I, then it makes that 25 longer. All right, so for this next problem here for City 1, City 2, these are what we like to call the postman problems. Because the idea is you have to find the most efficient route through each of the streets. So there's the same steps are always involved, and there are these 4 steps right here. So the first thing you want to do is identify the odd numbered vertices. So that's odd degree. So that would be vertex A and vertex C in the first city. So the second step is you want to find the shortest path between these 2 odd vertices. So what I like to do first is go ahead and look at all the possibilities from getting from A to C. I could go directly from A to C. That would be 12 hours. I could go from A to E to D to A. That would be a total of 20 hours, so that's longer, so that's not an option. I could go from A to B, which is 7 hours. Then I could go 12 hours and then go another 9 hours. And again, that would be probably a bad option. So the shortest route is to go from A to E and then E to C, which is only an additional 19 hours. So to draw the circuit, you want to go A to B to E to D to C to E to C again, and then you could go to A, and that would take you all the way around in the most efficient time. So in the second one here, we're going to do the same thing. We're going to find those odd vertices. Our odd vertices are C and E, and we want to find the shortest route. So I could go directly across, which is 6, but there's a shorter route if I go through B. And then you just write out the path. Make sure when you're writing out the path that you include these extra edges and that you do go through each vertex once. So I'm going to pause the video so you can write that out. That is your review for the Unit 7 test. So you can go through this before you take the Unit 7 test. Make sure that you contact me if you have any questions. You can either call, text, or email me for any information that you need.